Yeah, it's a recording. So thank you again, Carla. The word is yours. You can start. Yeah.
Okay.
And just
So,
remember that, sorry, that you can make questions in the chat. I will monitor the questions and make to Carla after the 30 minutes seminar. Okay, thank you very much.
okay, cool. Thank you, Professor Dennis. Thank you for inviting me to present some part of the work that we've developed between UNICAMP and the university. Thank you for all for joining. Good morning, everyone, or good afternoon, depending on where you are. And I'll present a work about Bayesian uncertainty analysis of oil reservoirs, mostly focused on how to deal with high dimensionality in the input and output spaces. So this presentation is mostly divided for, I'll just set up the scene with an overview of uncertainty analysis of complex models. Then I'll go into Bayesian uncertainty analysis, focus on the high dimensionality in the output and input and output spaces. And then I'll sum up and bring some conclusions. So first, I'd like to bring the concept of complex models. In many scientific disciplines, complex computer models are employed to help understand corresponding real-world physical process. Well, we have, for example, oil reservoirs used to manage assets associated with the reservoir in order to develop efficient production schedules, for example. We have climate change models used to assess likely effects of human intervention upon future climate behavior. We have disease modeling, for example, models used to study intervention to control infections and disease. So the use of complex models is used all over the place now, and we refer to these simulators as computer models. So basically, you use a computer model to make experiments and make inferences about the behavior of a real-world system. This computer model can be described as a mathematical function, f, that takes a vector x of inputs, representing the properties of the physical system. And you run the complex model, and it produces an output vector, y, representing the system behavior. Usually, we need to identify choices of input parameters x and assess how informative y is for the behavior of the actual system z. Often we make observations of the real system to perform an inverse modeling, and we estimate x given the observations we have. Now, however, each part of this process has its uncertainties that, if not considered, can lead to several problems, as, for example, overfitting, overconfidence, and so on. So I would like just to highlight some of the uncertainties that we have within this process. For example, in the input side, we have parametric uncertainty, as in many cases, a model requires a high-dimensional parametric specification. We also have condition uncertainty related to boundary conditions, initial conditions, and forcing functions. Now, when you go to the model itself, we have functional uncertainty. It can be too slow to run a model in the entire input space, so the function is unknown almost everywhere. We also have solution uncertainty. We can't solve the equations perfectly. Quite often, we have a continuous system that have to be discretized. Now, when we compare the model outputs with the real world, we also have structural uncertainty. This is an important one, as the model only approximates the physical system. This is the idea that your model is missing something. What's wrong? What's missing? Your model attempts to capture the main structure of the problem, but it will have something left out, and this also should be considered. Now, when we go to observations, and finally, we have the measurement uncertainty, as the model is calibrated against system data, and all of which is measured with error. So we have a problem. Within this contest, how do we perform calibration, which is the idea of learning about acceptable input parameters that provide good matches between outputs and historical data, generate reliable models to support decision-making, such as using them to forecast with appropriate uncertainty, and also How do we decide which future experiments to perform or which data we need to pay for? When we need to explore the entire input space to identify all possible combination of inputs. Even for a model that takes seconds to run, this can be unfeasible. We have a high-dimensional input space and output space, and also we need to consider all relevant uncertainties in this process. Well, to deal with this type of problems, an area of Bayesian statistics has arisen to deal with this generic problem and the many problems that they present. This area is referred to as the study of complex models, or uncertainty analysis, or uncertainty quantification. And it is mainly centered around the idea of emulators, which is a fast statistical approximation to the computer model that provides you not only the expectation, but also the uncertainty around this estimate. And with this tool that is extremely fast to evaluate, you can perform a full exploration of the parameter space and hence facilitate calibration, uncertainty analysis, forecasting, and decision support, and have been employed in a range of scientific areas such as cosmology, epidemiology, climate science, oil industry, and so on. Well, as you can see in the slide, the emulator is represented by a vector function, where in the case of oil reservoir models, the list of input parameters, such as porosity, permeability, is represented by X, and the active input parameters represented by XA, and f of x is the list of model outputs, such as oil rate from one specific well at a specific period. The first term of the equation is a regression term. The second is a Gaussian process representing the residual local variation, and the nugget is an uncorrelated term that models the effects of the inactive variables. Now, how can we incorporate uncertainties? Through the implausibility analysis. This analysis allows you to identify regions of the input space that are deemed implausible, depending on the objective of your study. And we need to compute an implausibility measure that is represented by this equation. This measure computes the difference between the expected output at a specific input value x, which is obtained using the emulator that you have constructed, and the historical data divided by a sum of variances that includes the uncertainty of the emulator, the model discrepancy, and observational error. So if you have large value of i's, it indicates that it is unlikely that the input vector will result in output that will match observed data. This input is called implausible, whereas a low value corresponds either to an acceptable input or one which we are still uncertain about. And this vector of inputs is called non-implausible. Well, the main difference from other probabilistic calibration approaches is that instead of looking at parts of the input space where the majority of the posterior mass is concentrated, it does the opposite. It looks for the parts of the input space where it is very unlikely to provide a match to the observed data. Now that we've got a brief overview of uncertainty analysis of complex models, some problems that we need to deal with, and one possible solution, I would like to illustrate the construction of an emulator and the calibration process using a simple 1D example. Say that we are interested in one specific output, f of x, that varies according to one input parameter x. And we have 6 evaluations of the model represented by the black dots, which we use to construct the emulator. This picture shows the output of the emulator constructed using the 6 simulation runs that we have. The blue line represents the emulator's expectation value of the output f of x, and the pair of red lines give the credible interval, the uncertainty of the expected output, both as functions of x. This defines a region between the red lines that we believe is highly likely to contain the true function f of x. Now, as the emulator is extremely fast to evaluate, we can replace the original model in any larger calculation and provide structural insight into the behavior of the model. Now, let's consider the uncertainty reduction process problem, and we need to perform a global parameter search to answer two questions. First, are there any input parameter x that lead to acceptable matches between the model output and observed data represented by the black line, the black horizontal line with observational error? If so, what is the full set of x that contains all such input parameter settings? And it's here that we need to employ the implausibility measure to determine the parts of the input space that can be disconsidered from further investigation. So we need to ask the question, for an unexplored input parameter x, one point in the input space that you have not run your simulator, how far would be the emulator's expected output value would be from the corresponding observed value? The implausibility measure captures this. The red part of the input space is considered implausible, meaning that it is unlikely that the output will match the observed data. And the yellow to green region means that the input is not implausible. That is, either it's acceptable input vector or one which are still uncertain about. And why is that? Because, for example, if you design a new experiment within the non-implausible region in green, you have another point, you update the emulator based on this new result and perform the implausibility analysis again, you will find a new region that is considered implausible. And each time you design a new experiment, we call it waves. You hear this word quite a lot over the presentation. And if you design a new model run, you update the emulator, perform again, and get the results, and with one more run. This can be done until your emulator variance, which is the case, is too small in comparison to the observed error. And at the end, you have all possible input parameter x that leads to an output that match observed data, in this case represented by these two regions in the x-axis. Well, now let's bring all this theory to the oil reservoir contest. Remember that these are the elements in the complex model analysis. We have model inputs. In the case of oil reservoir, can be rock and fluid properties, geological description, fluid contest, and so on. We have the reservoir model that simulates all properties of a reservoir under production, providing the outputs represented by these two graphs, which are, for example, water and oil rates for specific wells. And then we need to perform this inverse modeling and uncertainty reduction using real observations. What happens when you use emulators in this contest? Instead of running a simulator model, we use emulators to provide expected values of the output and the uncertainty of this estimate. And we perform the implausibility analysis to perform the uncertainty reduction. However, in this contest, we have among several challenges, two that I would like to address. We have high dimensionality, both in the input space, and that becomes a challenge to construct emulators with such a large amount of data. And we also have high dimensionality in the output space. This type of model can have hundreds of outputs to be compared with observed data. So if you imagine a field with 10 wells producing over 10 years, and you have information about fluid and pressure each 30 days, so imagine the amount of information you have. It's quite huge. So now I'd like to address actually these two problems. First, I would like to tackle the first question. I would like to try to answer how to perform an efficient and careful selection of data for emulation. Which outputs do I need to emulate? Well, within this process of constructing emulators, we need to identify those outputs and combination of outputs that provides you the highest information. That means will enable you to reduce the uncertainty of the reservoir. To do that, we propose to emulate all outputs you have, all available information that you have, using a fast version of the emulator that consider only the regression term, not the Gaussian process, which is extremely fast to compute. And you compute the implausibility measure to each one of the outputs. And with this measure, you can quantify the space cutout due to each output using two simple equations, okay? So for the first output, the one that is most informative, we compute the ratio of the number of parameter combinations considered implausible that you discard and the total number of combinations that you will have evaluated. Now, to obtain the following most informative outputs, considering that we selected the previous one, we compute the space cutout in terms of the remaining in space. So with these two measures, you can compute the space cutout and select the combination with the most, which are the most informative, which allows you to have the highest amount of uncertainty reduction. And with these outputs, specific outputs, you can construct a full emulator if necessary, because sometimes you already have an emulator with sufficient quality, and you perform the implausibility analysis, uncertainty reduction, and you go to the second and following waves through the whole process again. So we tested this methodology to a synthetic reservoir model, which was built using public data from a Brazilian offshore field. And the model is in early stage of development with 4 vertical producers. And we investigated a wide range of classes of outputs and objection functions. For instance, we considered cumulative data, rates and pressures at each time step, statistical measures, and time for water breakthrough. So at the end, we have a total of more than 2,000 outputs that could be emulated, and we need to select which were the most informative ones. So with this setup, we applied the methodology, and this procedure was performed in 4 waves. It was 4 iterations, and I'll present a summary of the results in the following slides. So to get a clear view of the uncertainty reduction of the input space, we use a pair plot colored by the density of the samples. Yellow to green is the gradation of intensity of the non-implausible inputs, and gray represents the area considered implausible. For example, if you fold these 3 first inputs, KX1, KX2, and KX3, you end up with the traditional 3D plot showing the distribution of the inputs in the input parameter space. Now, let's see what happens when we select the most informative outputs, construct emulators, and perform the implausibility analysis. So this is the input parameter space, how it looks like after performing the first wave, considering only 4 outputs from the more than 2,000 that we had. And this is the second wave with further selecting 6 outputs. This is a third wave, and this is the fourth wave. So you can see the progress of the input space over the waves and the uncertainty reduction of the variables. So this final input space shows a tiny part, actually, of the initial input space. Remember that we are in a high-dimensional input space. In this specific case, it was the input space was 14 parameters, which is also can be considered as high. And there was a reduction of more than 99% of the initial input space. And you see the uncertainty reduction in several inputs, but for example, take a look at KX6, which was a quite significant reduction on this variable. And it's more important, it's also possible to identify the structure and relationship between variables. Take a look at KX1 and KX5, where you have this curve. So you can identify this relationship with the variables using this methodology. But at the end, what we really want is to have reliable models that can be used for decision support. These are production graphs after simulating models sampled from the final input space, the previous plot that I showed. The color of the lines show the difference between the runs through the waves, and the black dots are the observed data. So we can see the significant improvement both in the historical period and also in the forecast period. And more importantly, we still have the uncertainty in the forecast period because with this type of analysis, you don't have overconfident actually results. You can have the all range of possible results. And we had this significant improvement and in a few waves. And we had the initial input space was reduced by 99%, actually constructing only 16 emulators from the more than 2,000 the outputs that we had available. Now let's focus to the input space. How do we deal with the high dimensionality in the input space? More specifically, how to include spatial maps, spatial properties in the emulation construction. This is quite a really complex task, and I will try to bring some ideas and how to tackle it. Of course, it's not finished. We still have a lot to do, but I would like to show you some ideas. We have 2 steps that we shall consider. The first one is what we've called screening step that aims to discard reservoir models that are not in accordance with historical data based only on the physical characteristics of the reservoir without running the simulation software. For that, we need to perform a reservoir behavior analysis. We need to explore and identify key types of reservoir behavior related to reservoir features. With this, we would be able to spot clear features of the maps that allows you to roll out a map which is clearly unfeasible in terms of mimicking the historical data. Then we can use classification models to also roll out models that are also clearly unfeasible. And those models that wasn't eliminated in the previous analysis. For that, you have a range of possibilities. You can use logistics regression, support vector machine. You have a wide range of possibilities here. And once we have reservoir constraints and classification models, we can apply directly to a new reservoir, a new propose of reservoir without running the simulation software. The next, after filtering out clearly unfeasible models, we can use canonical correlation as a dimensionality reduction technique to allow the use of map data in the emulation process. And what is that? What is the canonical correlation? What the canonical correlation analysis perform? Well, canonical correlation finds linear combinations that have maximum possible correlation between 2 sets of data. In this case, in this study, between spatial maps in the input space represented by this grid x1 to x20 and production data represented by the y vector from y1 to y5. In this way, it is possible to select sets of vectors U highlighted in green that are linear combination of simulation grid that have a high correlation with the linear combination of production data represented by the vector T. And we use these vectors U as inputs in the construction of the emulator. Now, with these vectors, we can proceed actually to the usual process of constructing emulator and perform the uncertainty reduction through the implausibility analysis. Now, we applied this technique. We tested this into a 2D reservoir with a channel structure, as you can see in this picture, that comprises 3 phases: a fluvial channel, a levee, and a shale in the background. So due to the time constraint, I will bring just a summary of what we have done. But first, to be able to evaluate a large amount of maps and reduce the time of generating these maps, we designed our script for fast proposal of maps that mimic a commercial software actually used to produce these maps. And with this, we are able to generate and evaluate millions of maps in a matter of seconds. And in the screening phase, we also created an R script to check the connectivity between wells. And we use this connectivity script to roll out models based on well locations, which were the constraints, and the connectivity between wells. And after that, we also constructed a classification model based on water breakthrough using as input parameters, that summarize the map, computed using this connectivity R script developed in the reservoir behavior analysis. Now, with these 2 steps, reservoir behavior analysis, construction, and the classification model, and we constructed a nonlinear support vector machine. In this case, we tested several, but this was the one that provided the best results. So after we filtered out unfeasible models, it enabled us to perform the canonical correlation. So we start the process with a full reservoir grid that in this case has more than 5,000 inputs. Then we upscaled the grid ending with 324 grid cells with using the mean values between 4 closed cells. And we applied the canonical correlation and selected 100 to 200 linear combinations, those vector U of that are considered as inputs to construct the emulator. And this picture shows the diagnostic plot of the emulator, just to have an idea of what is the quality of the emulator constructed using an input vectors of linear combinations. So I hope you can see we got like adjusted R square of 0.88, and this scatter plot shows predicted values on y-axis and true outputs, and shows that the blue line, which be the perfect match, is within the uncertainty range of the majority of the test points that we have. So with these emulators, we performed the implausibility analysis and uncertainty reductions. And these are the results from the first wave only, okay? So this is just the first wave. You can see that we already have improvements on the results, but we clearly need other waves that need to be done in order to obtain reliable models to be used in forecast. So just to sum up everything, how can we properly address uncertainty of complex models? Well, you can use emulators to mimic model behavior and implausibility analysis to look for parts of the input space that can be discarded with the capacity of including several sources of uncertainty and have computational efficiency gain. How to deal with the high dimensionality in the input space. You can use a measure that computes how informative an output is using that space cutout measure, and select the combination with the highest space cutout. This method provides an efficient and careful selection of data to be emulated. How to deal with the high dimensionality in the input space. Previous to any dimensionality reduction technique, a reservoir behavior analysis is essential to rule out maps which are clearly unfeasible in terms of mimicking the historical data. Classification models have also the role to remove unfeasible maps. However, we need to pay attention to false positives, wrongly rule out, for example, a feasible map. And it was possible to construct classification models using summaries of the map data, it wasn't necessary to use the grid cells. And the canonical correlation technique reduced the dimensionality of the problem, and it was possible to construct emulators using linear combination of grid cells from the spatial data. And looking ahead, we still have several challenges to address, but just to highlight some, we need to scale up to 3D models. I tested in a 2D model. We need to test different types of model structures, such as one homogeneous structure, or those that present high heterogeneity, such as bugs, fractures, and so on. Instead of using grid cell properties, we can use the petrophysical modeling properties, go one step back to construct emulators, and many more. So thank you for your attention, and soon the floor will be open for questions. But in any case, you have my contact if you want to reach me and have more information. And also, I'd like to thank all our sponsors, and of course, in special, Professor Dennis, Avance, Luciana Maria from Unicamp, and also Ian Werner, Michael Goldstein, and Camila Caiado from the University. So thank you very much, and let's see the questions.
Thank you very much, Carla. It was an excellent presentation. We have a question from Marcelo Zampieri. He's asking about, he congratulated for the presentation, and the question is, how does the emulator deal with human intervention, like shutting due to high GOR, water cut, and operational issues? And he has a second question. Maybe you can answer the first one first, and then I'll talk about the other.
Let me think. We also have Ian Werner. Hi, Ian.
Hey.
Hello, Ian.
Hi.
Well, I'm just thinking about, hi, Michael.
So is it possible to incorporate human intervention in these emulators? That's his question.
It's a very good question.
Yeah.
To start with. I would, my first response would be to say that the emulator's role is to mimic your model. So you have a reservoir model that you've spent time and effort building to be as accurate as possible. So the real question is, how does your model deal with human intervention? And so if you were running your model and you suspect you're going to have a shut-in decision, you may code that into your model. So the emulator will just try to mimic that. Now, knowing about that, of course, if you know about that in advance, then yes, you might want to build your emulator construction with that in mind. So things like this, where you suddenly shut things down, would lead to the function that you're emulating having a sudden change in form. When you say you increase some parameter, your production goes up and up, but then you shut down. So now your production is either like cumulative is at a plateau, or an oil rate is now dropping off a cliff. So if you know about that in advance, yes, you could build that into your emulator. There's emulator forms which have sort of discontinuities built in, so they know to sort of anticipate such a thing. So that would be my first thought. There is much more to say on that, but I don't want to go on for too long.
Yeah.
Thank you. There is a second question from Marcelo, which is how to deal with anomalies and outliers. Also important.
Yes, I think this is one of the reasons that we do the reservoir behavior analysis before actually going to the emulator procedure itself, just to remove these outliers, which would be like those clearly not feasible maps that would be enable actually for you to get perform actually the canonical correlation, or either construct the emulator and get high quality emulators.
Okay, Alessandra has a question also. It's very nice to hear it from you. He's just saying, very good presentation. And she's asking about the time consumption of the process. How do you compare the time consumption to generate the emulators and then to run it? compared to the traditional way using the simulators?
Yes, I got some numbers here. I was going to be prepared for that. So yes, actually to construct, for example, the emulators, we needed, of course, we need simulation models to construct emulators. For example, in these cases, we had a setup of 500 of models to construct. So it's just in terms of how many models you need actually to construct your model. But once you have the emulator, the full process is extremely fast. So for example, I ran in this case with the channel structure, 5 million possible maps, ended up with 300 scenarios at the end, which were like approved. And this full process, when it's set up, it takes 30 minutes. So it's quite fast. So it's just a matter of, I think the most time-consuming part is to construct the emulator itself, because it depends on the number of simulation runs that you have.
Thank you,
I
Carla.
don't know if I answered.
Of course, if there is an additional question, you can ask to Carla. I have a question here, Carla. Can you talk a little bit more about the overfitting and overconfidence that you have? You mentioned that in your introduction, and I think this is one of the problems that we have to incorporate in our methodologies, right? Yeah.
Yes, of course. For example, if you do not actually consider uncertainty, for example, in the model itself, and observational errors, you end up with just, for example, a few number of input parameters that actually fits your data. But if you measure the data, again, you have a new observed value, and that input wouldn't be acceptable again. So in order to avoid overfitting, you need to consider the uncertainty in the observed data, and also uncertainty in the model, which would be the model discrepancy. Now, talking about overconfident, it's the thing, usually what people do is an optimization procedure. You're looking for the best matches, so you end up with a few runs that match with your observed data. But imagine that your plausible space is composed from two different regions, and those two regions have totally different forecasts. And you find a few simulation runs within just one region. And this region is totally different from this region. So you miss actually part of the story. So you ended up with a forecast that not represent the full possibility of outcomes. And that's why instead of chasing for the best model, we try to do the opposite, actually. We try to rule out what it's unlikely to happen and keep all the possibilities that are still likely to happen until we have further information.
Okay, thanks. And a question related to that, I think the answer is related to that. And when you showed your slide 35, you don't need to go back to the presentation, but you were comparing the UNISIM one case that you run, and you show a red dot, which is your true answer, right? And in your case, it was an hypothetical solution, right?
Yes.
I'm very interested in how to extend these results to real case. What do you think it's important, because you have some experience on that, trying to put the real data there? What's important to consider, for example, when you have a model, you have your uncertainty, you are doing this, but you didn't consider the full range of uncertainties, you don't have a hypothetical reality. How do you think it's different from your process in the UNISIM one?
Yes, I think two major sources of uncertainty are, of course, observational errors that we included in the process. But what we have not included, but it's extremely important, especially with real data, is the model discrepancy. Because even though you find actually the perfect outputs, your model wouldn't be represented the real world. So, and this model discrepancy is like divided with internal discrepancy, which is the simulation model itself, that there are some techniques that you can compute that, but you also have external discrepancy. I don't know, Michael, you want to bring more information about that because you are a really expert in that. You're muted.
Okay, so model discrepancy, yeah. I mean, building models is a fine way of exploring what will happen, but to actually use it to say, make a statement about the real world, which you commit real resources for real outcomes, the model is just part of the story. And if you ignore that, then the reliability of what you have. I mean, so for example, the whole world is undergoing a pandemic at the moment. It builds models, and the models make statements. So people then react to them, but the models are just models. And okay, so let me say something more specific. Okay, there are particular ways, systematic ways of generating and understanding the discrepancy in models. So we divide everything very strictly into notions of internal discrepancy, things that you can find out about the way your model relates to the world by essentially operations and computer experiments. And we completely recommend strongly that you do this to understand how errors in the model now under forecasts now project into under forecasts in the future. You can do this by experimenting and understanding sort of the weaknesses of your own system. And then there's external discrepancy, where we talk about thinking about all the features that you know that your model misses and making probabilistic representations for them. See, I've been doing this for a very, very long time. And so about 30 years ago, when we first got into this, okay, so the first curve we were ever shown, we were shown a pressure profile that was dropping, okay, and in the model, and a pressure profile in the world, okay, and effectively, and the pressure profile in the world did not match the pressure profile in the model, but there were many different ways it couldn't match, and they were very happy with a model that systematically underpredicted, because they understood that underprediction. They said, well, the oil reservoir, I mean, the model moves the wells about a bit to be in the center of cells, so time is always offset. So effectively, if I get it a bit wrong now, I can see how to extend my curve. Another model which actually fit, they actually did it better, but crisscrossed. They hated that because it didn't represent to them the ways that the model differed from the system. So the notion that the model is not the same as the system and that needs to be represented, you know, is just fundamental, and it should go through everything. And it tends to be a bit of a missing ingredient. Sorry, I said too much already. Yeah.
Thank you, Mike. But I don't know if anyone has additional questions. Here is another one from Sampieri. One challenge that you may be facing applying emulator is the amount of data and years of production. Is it possible to use emulators in green fields, like fields that have just 3 years of production and sometimes not too much water production and so on?
Let me think. Yes, indeed. Of course, the amount of uncertainty, actually, I was asked this question, actually, I think yesterday, the notion of green fields and brown fields because of the amount of data that you have. But I think it's just a matter of the uncertainty that you have, actually, because in a green field, the uncertainty will be higher due to the amount of information that you have. That's why you need to consider uncertainty in the process, because the emulator will give you the expectation of the output, but it will give you the range between those red lines where you think it will be a line between. So over when you progress and you have more information, you're able to reduce those red lines and reduce the uncertainties. So it is possible, indeed, because you still have the uncertainty range in it. Ian?
Could I just add? So I think Carla's actually nailed the main point, but that there is often this sort of confusion that you need a lot of data for the emulator. The emulator is just mimicking your reservoir model. That's its job. It mimics it with uncertainty. So the question is more, are you using reservoir models for greenfield sites? And I imagine, yes, you are, because you use reservoir models to predict what a greenfield will do and to plan various management strategies, et cetera, et cetera. So anywhere where you're using a model, an emulator will come in and give you this massive speed boost. It gives you multiple orders of magnitude speed boost. So if you wanted to make, say, more accurate predictions about what the greenfield site will do, your emulator will help you do that. Or if you want to decide between different operational strategies, your emulator would help you to do that. So it does not need any production data at all, because it's not really based on that. The implausibility stuff uses production data, but the emulators just give you a speedy way to mimic your reservoir model itself.
Yeah, it was a nice concept. Another question, since people don't have questions here, I'll ask another one just so. When we do in real life, we have cycles, right? For example, you realize you do a procedure like you showed for UNISIM 1, and 6 months later, you have more data, you have everything again. So are you? We are facing some problems in cycles in other methodologies. Just trying to decide if it's when you do a next cycle. Do you use only the new data, or you have to go back and use all the data again and do the whole process again? Because in a perfect world, the new cycle would just reduce a little bit more the uncertainties, and as you go in the future, you keep reducing. But in a real life, when you do that, the uncertainty reduction you do in the first cycle, when you use this data for the next cycle, sometimes the data is a little bit out of your reality, and then you have problems. So what do you recommend for these things? Do you always go back to the initial of the time and do the implausibility analysis considering the whole set of data? Or is it possible to do using just the first cycle results and don't perform again? I don't know if it was clear, the question.
Do you want to say something here?
Oh, that's a really good question, Dennis, and I would love to talk all day about that. But Carla, would you like to say a word, or do you want me to jump in? I'm happy either.
Yeah, just go. That's fine.
Okay, no, it's a really good question, Dennis, and it's something which plagues a lot of approaches. You bring in new data, as you say, in a new cycle, and suddenly you find that data is annoyingly inconsistent with your previous analysis. Now, the key thing is practically on the ground with our approach. We would hope that would not happen, but of course it could happen. But for our approach, it's okay. The emulators have already been built for all the previous time points, so we can go back and revisit the original analysis if we want to, and perhaps expand some uncertainties. I'll get to that in a second. So to go back and kind of redo the analysis is not too bad, because you've kind of done half of the analysis already. You may need to do a few more runs to maybe do another final wave or two again. But you can reborrow a lot of your analysis. The way the implausibility works, you can kind of reborrow. But the key issue, of course, is why this would happen in the first place. And this happens typically because, of course, the uncertainties, which are hard to specify in some cases, have been underspecified. Or, for example, as Michael was talking about, model discrepancy is somewhat neglected. So what we often do with our analysis is we start with fairly large conservative uncertainties. So by conservative, I actually mean big in this case. We rule out all the input space and then make predictions, and then we would hope that the next phase of data is not inconsistent with those predictions. If it is, it means that we specified an uncertainty which is too small. So we can go back. Going back is not too much pain here because of the way we cut out space. But we would hope with that putting that model discrepancy in, we would hope to be in that situation far less often. But I can't say to you that it will never happen. That would be too arrogant a statement to say, even for me.
Yeah, but we could make a further comment though. That the question about whether it is inconsistent or not, okay, depends on whether. So you have restricted your input space to a collection of potential models. Now that potential collection of models is still quite large, and it has quite many funny shapes in. So the question about whether you've now just got some even more informative data that have even further restricted the space, but it's now hard to search. See, quite often it's the case, I think, that people think that it doesn't get a match because they're not good at searching small, high-dimensional but structured spaces. So they wrongly think that the data is inconsistent rather than dead informative, but requiring you to shrink to an even smaller space. So, I mean, mostly I think probably people are just missing the chance to really explore their space very carefully. And there's a lot of mileage to be done in that.
Yeah, thank you. I agree completely. Yeah, and in our problems, when this type of problem happens, is because of the unmapped uncertainties, the uncertainties that were not considered initially in the problem. That it can happen in the real world because companies are doing that very fast, and so we have to have a solution to that. But it's not fault of the implausibility analysis; it's the fault of the uncertainties that were not mapped correctly in the beginning of the process. I agree completely. Yeah.
Yeah. So I think if people use bad forecasting methods, they will then make bad forecasts that won't agree with what they see in, you know, when they actually look. But the whole point is to replace it by good, careful forecasting methods.
Yeah, I agree. And the forecasts don't depend only on the models, right? Depend on all other things that we have to consider as well. So it's very hard to do it. You know.
Yes, indeed.
That we are trying to separate here. I had a discussion this morning in a human intervention tree forecast, which is one case, and when we have a human intervention, it's completely different thing, right? Completely different thing. So, yeah.
Yes, that's a even more fun game when you start forecasting into the future with human intervention.
Yeah.
But again, and Michael's done some papers on this about emulating sort of decision structures and choices of decisions. That kind of falls into that setup. But you're right, there's a lot of other things to then consider, perhaps to emulate or to have uncertainty over, to analyze that. And it's an even more fun game, I would say.
Yeah, for us researchers, it's much better like this way, right? We have a lot of things to do. Okay, I don't think we have additional questions. So
Professor,
I don't know.
I have one
Yeah,
question.
sure, Guilherme.
Hi, Carla. Nice to meet you.
Hi,
Nice to see you again. Hi, Michael.
Hey, Guilherme.
Okay.
Carla. Yeah, Carla, thank you so much for your presentation. It's not more a question, but it's a point that I would like to comment, and it's for us for people that don't have an idea about emulators, because Bayesian emulators has been used for a long time in a lot of areas, including biological system, galaxy formation. That Ian and Mike have a great paper explaining how to use emulators, climate, oil reservoirs, and etc. And also, Michael presents the Bayes linear that's save a lot of time, work with expectation, also variance. As Carla presents, it's just based on Bayes linear, right? So I would like to say thank you a lot for Michael, Ian, Carla, Elena, and Luciana, everybody that is on board in order to solve all the problems that we have in our oil reservoir. So this question that I have is in order to try to explain for people that doesn't have an idea or are in contact with emulators, how powerful this technique it is. So I would like to mention a little bit about also for Ian, Carla, and Michael, the difference when we compare with the artificial techniques that is increasing a lot, and that is just based on statistical approach that we use a lot when we build emulators, from simple case for complex case. Just can you explain or give an idea about when we compare emulators with artificial techniques that people are using a lot, and emulators has been used for a long time also, and just a comment when we use both techniques, please.
Yes, well,
Carla.
I have been seeing some wave on the industry also to go to hybrid models, actually, that you have data driven and also physical model based, because once you go just to data driven models, you can miss the physical insights of the problem, and you can get, actually, it's like a black box. You don't know what happens, what is just going inside, and you don't have control in it. So we can use the power of data-driven models when you have like a lot of data, but you need to do it in a careful way, considering the uncertainties and everything which is involved in the process. So I don't know if Ian and Michael have more to add.
Well, yes, yeah, I think Carla sort of mentioned the main thing. I mean, there are various things people can do. There's various things people try to do, and there's a lot of sort of fashionable excitement about various methods, sort of machine learning type methods these days, or there are just straight up statistical sort of data methods where you just, you know, fit to your data and extrapolate forwards. And the key thing, the sort of analysis we always try and do, and I wouldn't want to ever say certain areas are bad in their entirety or anything like that. There's always some good parts to each area. But the principle we try to stick to is doing an analysis where you understand what's going on, where you can point to each part of your analysis. When Carla showed the emulator equation, you can break it into even smaller pieces, and you can point to a piece and you say, this piece is doing this. And I can track that through the calculation. And I can say that piece tracks into here, increases the uncertainty here. It moves my predictions for oil production at this time period, and it cuts out this input space, which reduces my forecasting uncertainty for this region. So I can track through everything that's happening. So everything you can look at and you can poke and you can therefore justify and you can have confidence in. Now, I always get nervous about approaches which just use, say, a sort of standard machine learning approach, which uses a lot of data to train an object which will give you certain predictive capability, unless you have a really large amount of data and you just trust that it just can't really go wrong because you're swamping it with huge amounts of data. But for complex models and complex systems, you may think you have a lot of data, but you don't really. So I get very nervous about any approach where you can't open the box and say, why are you acting the way you're acting? There I am talking to my algorithm, incidentally, when I speak like this. So any approach which doesn't do that, I get nervous about. Now, an emulator is just a construct that helps you use your reservoir model that you care about, helps you use it better, because it just helps you to evaluate it much, much quicker. And it fills in space between your evaluations that you've made. And it has the idea that your reservoir model probably has some concept of smoothness at certain parts, not always, but at certain parts. So it just allows you to do a more sophisticated, nuanced analysis, the sort of analysis you would like to do if you had time to write a physical model. So I just say those are the principles we try to act on, and that's the kind of, it drives the direction we use.
Yeah. So just a couple more things, I guess. I mean, a model could take a second to run, or it could take 2 days to run. Now, emulators take, I mean, once you've built them, just take the same amount of time helping you to support a 2-day model or 1 second. Yeah? So the relative increase, I mean, the slower the model, the more important it is. Also, however, there is basically insights that you can find by building your emulators. For example, if your model is slow, you might relate it to a fast model, and then you might say, how can I relate my fast model to my slow model? And it's much easier to build relationships between emulators than it is to build a relationship between models, because all you can do with the models is just talk about a difference, but the emulator is structured so you can build a relationship for it. Then if I want to then talk about my structural discrepancy, which I always want to do, and I want to understand how does my model differ from the world, it's much easier to understand how my emulator, because it's an explicit structure, differs from the world, and to represent that than it would be to represent how my model differed. So there are fundamental values from building the emulator, plus there's the extra value in, however, the slower the model, the more valuable the method is.
Yeah, thank you so much, Ian and Carla, and also for Michael for the great answer. I think is, yeah, you explained the main difference and give us what is the emulator, the importance of using emulators. That is totally different. We have no comparison. As Ian said, we have pros and cons, use all the techniques in the world, you know. Thank you. Yeah, thank you so much.
Okay, thank you, Carla, Michael, Ian, for the contributions. The idea here was just to give a flavor for the rest of the group, what we are doing in this kind of research. So if you have additional questions, I think you can send by email to Carla and Avanci and myself. Then thank you very much for the questions, and thank you everybody for participating today. See you next week. Bye bye.
Thank you. Bye.
Very much.
Thanks, everyone.
Bye-bye.